Yeah, can anyone confirm? Yeah. Okay, fine. Okay, okay. Yeah. Okay, okay, fine. Okay, yeah, sure. So, should we get started now? Hello. Am I audible? Hello. Am I audible, right? Okay, fine. Okay. I think let's just get started. So, uh, Meenakshi, can you mute yourself? Maybe I think. Mute. Okay. Okay. So, let's just get started. So, this week content was mostly about this uh, the basic. So, is there any doubt from session up to now? Even from, because this is the last session before exam. So, if you have any doubt and if you have any from previous any previous session, you can ask now. This is a better time to ask. Okay, so I think let's just get started. So I will just give you a very brief summary of this week content. So let me so this week content mostly about the active circuits. So which are your amplifiers and your oscillators. And amplifiers because these are active circuits, so they need some kind of power feeding to that. And basically amplifier is a device which amplify your input signal. Let's say your amplifier is, if you put amplifier, if you have a input signal, so then basically it just get amplified. So it's basically the multiply your amplitude of the signal. And how it is does it does not have any magic. So all the passive circuits actually that can't amplify your power. So like the passive circuit, if you take any RC circuit or RL circuit or RLC circuit, if you fed any input signal, they can enhance or either voltage or they can increase the voltage or current, but not both together actually. So then basically for the so your power is basically roughly, if you talk about the power, so it is multiplication of your voltage and current. So basically passive circuit like transformer or RLC circuits, they can't amplify this product actually. So one will get increased, other will get decreased actually. So your like if your circuit is lossless and it does not have any loss, then basically it can't amplify the signal actually. So so basically like the what if so what differ yeah. So, what differs from active circuit from passive circuit? They amplify the power. So there is a amplification of power. Not just so even the transformer also does like transformer is a kind of passive circuit. What it does is like it can suppose these are schematic of the transformer. So let's say your difference in the winding of the primary and secondary coil. So basically, it can either step up voltage or step down voltage, or vice versa, step up current or step down current. So, but the ideal transformer can't amplify your power actually. So, for power amplification and to boost your signal, you need some kind of active circuit, which especially at high frequency, those are amplifiers. So, then basically you can in your circuit basically you can define amplifier, and this also amplifiers. How does amplifier take energy actually? Suppose if you take calculate the power, and if you integrate in time, then basically you calculate the energy. If you compare the input energy in the signal and the versus output energy of the power amplifier, basically you will find that there is a proportional enhancement in the energy of the output signal. So where that energy comes from? So basically that comes from like you use for amplifier, you use the DC biasing actually. So that DC biasing actually, so the that energy what you are adding in the output signal is basically coming from your DC bias circuit which you are applying. So for that actually for active circuit like that DC biasing is become essential actually. So without that you can't have much amplification. You can't have power amplification per se. You can amplify voltage or current, but not the both as together. So basically like that. The problem with that's why that DC bias is absolutely necessary for to amplify the to like that all the energy comes from the your DC bias. Also, like the one important part is the DC bias. Let's say we consider a very uh, simplistic. Suppose we want to mix DC and high frequency signal. So DC biasing also helps in separate DC and RF signal. So that also helps. And basically also you can varying the DC bias, you can just operate in different region actually. Let's say you are like very simple amplifier if you are considering. So let's say this is MOSFET based amplifier, and this is, let's say, this is emitter, this is collector, and this is your gate, and you have apply a signal, uh, and then basically this is your RS, so load output. This is your VCC, basically that, and this is your RL. So basically, so what this amplifier does is, so this transistor what it's sitting. So this is the common emitter amplifier. So this is the most simple amplifier circuit which you see, and that basically if you so this is the gate, this is source, this is drain, and basically your drain current is ID is I drain to source current is a function of V gate to source voltage and also V drain voltage. So basically like whatever the drain voltage you apply, and also the what is the gate voltage you apply, your drain current is a function of that actually. So if you see like the characteristics of the transistor, so basically like the ID, so this is IDS, basically this current which is flowing through the drain to source. So from this terminal to this terminal, this is IDS, and that basically you can plot in terms of VGDS. So this voltage across this terminal drain and the common terminal, what is the relation of drain current actually. So that is this, these are known as output characteristics. Also there is a function of what is the so ID is also a function of your input voltage characteristic. So that is known as your transfer characteristics. So in MOSFET basically, so what has happened is, so the MOSFET characteristics are like this. So these are basically, if you increasing the so like these different curves correspond to increasing the gate voltage, gate to source. So VGS you are increasing, and this line is basically, this line is for fixed gate to source voltage, and this so also there is, once you fix this RL register, so this circuit, outside circuit, you can just assume a current, and basically you can draw a line in that linear circuit, that is known as the load line. So if you draw that load line, so this will come like this. So if you draw a load line, so that will come like this. So this is known as the load line. So now what will happen? So as you vary the gate voltage, let's say you apply a DC signal. So you apply a DC signal. Let's say you apply a DC signal, and on the top of you apply a AC signal. So that basically DC plus AC. So DC decide which point you are operating. Let's say you choose different value of so different value of VGS and VDS. So these are DC current and voltage. So different value of VGS, you can choose these different curves. So basically, like let's say if you are choosing this curve, if you are choosing, let's say, let me take a different pen. So let's say if you are choosing a this curve, and basically then your like at this load line the point is there, and that will correspond to VDS at this. Similarly, you can choose at other point also. So depending on which region of operation you want, or so that amplification basically you can achieve in different kind of, or if you change the load line. Let's say let me draw a few more characteristics here. So these are different, let's say these are different VGS equals to 0, VGS equals to, let's say, VDS. Then basically like these are different kind of characteristics, and if you change this load line, then basically you can operate in different regime actually. So if you change the value of RL, then basically you can operate in different region. So now let's say you change your gate to source voltage, which is this. So you how the amplification is, you choose a particular value of DC current at DC voltage at gate, and output DC current. So then basically let's say you choose the DC voltage corresponding to this gate to source voltage. Let's say this is VGS equals to zero point 0.1 volt, or let's say zero point 0.7 volt. Now this will follow these characteristics. Now this depending on, and these load lines will vary as you vary the RL. So basically the resistance of the circuit. So that if you vary, then basically uh, just then basically you can not, this will not, if you sweep the RL, this will not be parallel, this will not be parallel actually, this will move like this. So these will have slope. So let me just draw correct. So yeah, so if you change the RL, basically this will go like this. So as you change the RL, so you can have like this triode region and saturation region of the amplifier actually. So depending on like what gate voltage you choose. So if you are choosing this curve, so basically like if you vary the voltage around that this Q point, basically that is known as the quiescent point. So basically if you choose this point, so basically your input signal vary around this point. So this point around whatever the amplitude of your voltage, so the input signal will shuttle between these curves. So as you can see, like this after a certain threshold, so this is VGS threshold, the drain current will be zero on. So that basically like this, if you vary this voltage across this, so basically this voltage will get vary as you vary the signal voltage, but the current in this branch will vary according to like this. It will vary for half cycle, other cycle it will be zero, for half cycle only it will. And as you keep moving this point up and up, this conduction and angle will keep on increasing. Basically, now you can use more than half cycle, and then you can one point will come where you can use the different kind of half cycle. So basically, these if you are like that conduction angle on which your current flows, so that is known as the conduction angle. So you can classify the amplifier based on the conduction angle. So if that angle is whole 360 degree, so minus 180 degree to plus 180 degree. So basically, like then your then your conduction and angle is basically like this. So yeah. So then you can choose this 90 degree minus 90 degree plus 90 degree, that is 180 degree, and that is 45 degree minus 45. So basically like different kind of conduction angle you can choose, and then basically you can decide what kind of amplifier you want to have. So basically different conduction angle. So let's say if you are having uh, one less than 180 degree angle, so this so this hole will have the class A amplifier. So this, if your conduction angle is whole 360 degree, then this is known as class A amplifier. And if your conduction angle is between 360 and 180 degree, so then that is known as the class AB amplifier. And if your conduction angle is between this 180 degree, that is known as your class C amplifier. So it just conducts for half cycle, and beyond this you can have just D and E class amplifier. And this between this region, there is a class AB amplifier. So those kind of amplification and different kind of amplifier circuit you can achieve with the active circuit. So basically, the summary is you need to apply the bias and the and your signal voltage. Based on that, you can operate in. So DC bias will decide which region of operation you will operate, and that will basically lead to your like different amplification factor, or even gain will be different as you can move. The gain is yeah. So as you can see, like here the gain is different and compared to here. So this slope basically like the gain and those parameters also you can change. So there are different kinds of amplifier region operation you can operate. So up to now, is there any doubt whatever the content I have presented? Hmm. 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 Uh, in software, you means which software? Hmm. 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 Okay. Hmm. Okay. So basically, like see, like that, whatever the transistor you may use from like the different PDKs and the different technology node. that has your like this, whatever your current versus voltage characteristic na, that may have your the model corresponding to ID as a function of uh, V drain to source voltage and V gate to source voltage. Some other also parasitic parameters like substrate voltage and those kind of voltage also is there. So depending on like what is your like what is the Gaussian current, and like and the for that model actually the GM also will be GM of your GM basically is equals to del ID by del VGS, given that VDS is constant, right? And R naught will also be there del ID by uh, del VDS, given that VGS is constant. So this GM and R naught basically are two quantity for deciding the gain actually. So that basically also your input separation circuits and those like those can act as a low pass and high pass filter. Those also so based on like these are GM and R naught are basically transist like the intrinsic characteristics of the transistors. Now once you have chosen the transistor, your these characteristics are fixed. So now like once you have chosen the the particular model, so basically now like you know all the relation between ID and VDS and VGS, right? So now and also you can find GM in terms of VDS and VGS, you can find, so whether it's flat VGM and different regime of operation if you operate, then basically your VGM also varies. So like if you operate and this and like the if you operate like this ID versus VGS, you operate or for its fixed VDS, basically the gain gain peak comes in between actually. So the different region you can choose. If you want to choose a flat gain profile, then you just choose the top of this. So you if you want to get maximum gain, then you choose your point here actually. So that once you have decided the GM, basically this curve is given for your model, and then once you have R naught, that will decide your output characteristic. That will decide your this slope of this line actually. So this line will have this R naught. So for each increasing weakness, R naught will get increased. So that also you can use to quantify your total gain which you will get from the circuit. So once you have chosen the this point, and now whether you want to design a class A amplifier or B amplifier, so basically you want to operate at a certain points actually. So if you want to operate in the linear part, then you will operate at here. If you want to operate like let's say class B or class C amplifier, then you fix your quotient point there. So then basically you can choose your load line actually. Then basically external circuit parameters you can choose, and based on that you can just get the design parameters. Then accordingly you can design your registers based on layout, and then basically you can get design your circuit. So even after like once you have finalized let's say the tuning, so little bit tuning you need to do in layouts and those things, like especially in RF and analog, like all the placement of the components and different length of the metal lines, wires, and those also plays it quite an important role. Even so, for a very small kind of circuit, also you need to optimize a lot for analog RF circuits, like especially like all the impedance matching and input and output matching networks, and that should not cause instabilities, and that is like it's a quite complex design procedure. It can't be explained fully in one like very short time actually. So I hope it's clear. Yeah. Hmm. Hmm. Ah. Hmm. Ah. That. Yeah, that is fixed by your like physical your transistor process. Like that is limited by your physical process actually. So that okay. No, so basically you will have like the GM versus frequency will also be there. So GM versus frequency will also be there. Suppose you want and like for different frequency, different region may be there. So let's say at frequency something like this kind of flat thing is there. Suppose you want very flat gain profile, then you will operate in this region. And suppose you don't want, you can compromise the gain profile, but you want to operate at different frequency region. Then you can operate in around region. But if you need broadband amplifier, then you need basically flat GM versus frequency. So basically, you will, if you see the GM versus frequency curve, then basically you just want to operate at the like at the frequency which range you want your gain is flat, or like if your gain. Okay, so just let me know. Now is it clear? Uh, now how is it? Okay, so basically like your GM versus frequency curve also you can decide. So basically, if you want a very broadband kind of amplifier, then basically you need like very flat GM but compared with respect to frequency. Or if you want gain constant, so basically like that GM is basically like GM is a function of VGS voltage. So this peak. So if you have very flat GM profile, so basically then like if you choose this region, then basically your GM will remain flat for different value of VGS actually. So that different value of VGS you can have like you can have different gain profile. You can control the gain based on by choosing appropriately the gain because total gain. Then basically you can have like varying like gain like the you can have like a large range of quotient point which you can choose, and basically you can have the flat gain profile, and your gain within that like a region of operation will remain constant. Also, like if you have very flat GM profile, then basically this all this curve and those things, those cause non-linearity actually. So if you like let's say if you like if you are sweeping the like if you are applying the signal basically, then you are changing the gate to source voltage with respect to the quotient point. So if your gain varies around that point which you are operating, let's say if you are operating at this point, so your GM varies around this point. So basically, this will cause a non-linearity actually. So then you will see the harmonics in the your output. So basically, like that is the trade-off, like which you want to have very low noise or you want to have very high gain. That trade-off you need to optimize, like which particular specific thing you want to have your amplifier here, right? So basically, all these transfers and output characteristics are fixed by the process actually. So different companies like for example, like different kind of PDKs are there for Intel, like this SCL PDK and TSMC PDK, or other companies like Global Foundry PDK. Like they have different characteristics, and based on those specs, you need to your characteristics will also get them. Also depending on different length and width of the parameters also you will get. So in those PDKs basically you will find that like how the your characteristic will change if you sweep other parameters. That you will specification you will find from the library files of that specific foundries or specific vendor, and then based on that you will start designing your circuit, and you optimize your circuit so that you achieve the like desired gain value, desired frequency range, and desired like operating point you want to operate, and desired like all the specification which you require, you can optimize your circuit based on that. Yeah, yeah, yeah. Accordingly, you need to set. Hmm. 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 Then you will design your output circuit. Also, this transistor will have frequency, all the parasitic component in this. So it may also have intrinsically also frequency dependence on the characteristic actually. So that also you need to take care on account, like especially in the analog RF, even designing with 10 20 active elements is very difficult actually. You need to do a lot of optimization. That's why it's quite hard and like quite time consuming. Or even after, let's say you design properly, so then also your spec will not meet. Then also you need to do multiple iteration, like how you can change, or let's say some foundry process is not correct. Then basically you need to design the circuit, then measure the device characteristics, all the like input output characteristics, all the load power load pull measurements, and those gain measurements you do. Then basically you can tweak the your circuits and amplifiers and different kinds of even the length and width of the transistors you can tweak. And then basically like that like your tolerance you can set in that actually. Like with the designs. Mhm. Load pull is basically you need to like impedance match, and then you need to terminate with the impedance, and then basically you need to apply a power, and then you just measure the power at the output. Because see, like for low frequency amplifier, you just need to just connect the wires and just oscilloscope, that will work. But in high frequency in gigahertz range, that will not work simply actually. So at each of the frequency, you need to match the input and output impedances actually. So that impedance is like sometimes like the proper impedance matching and proper region of operation you need to operate. Then basically, then only you will be able to measure the correct power which is going out from the amplifiers and the circuit or device which you are testing. Yeah. Okay, so basically, so in the high frequency, like high frequency case, actually, because see, your impedance is a function of your wire length and those things. Suppose you are taking a different probe and different design you have tried, let's say, like different routing wires you have used. Then accordingly, you need to match that impedance to that routing wires, and then only you can get power output from the amplifier. Otherwise all the power will get reflected back into the amplifier, or that may cause the instability within the amplifier, or amplifier may also get damaged if you are not matching impedance properly in that case. Yeah, so basically, the probe which you use for this like measuring the load, that will have also has a impedance. So that impedance, that characteristic impedance of that probe, you need to match the output impedance and input impedance of your transistor circuit actually. So for that, basically, let's say you have, huh, huh. Yeah, so but the thing is, if you change, let's say you change the length of the wire, then basically your total like output impedance will get complex impedance. Z in or Z out will get changed if you change even the slightest length in wire, depending on your frequency of operation. So basically, then your input impedance matching get disturbed. So to measure with that design, you need to again impedance match and tune your impedance matching circuit so that you can measure the power actually. Yeah, so that will not be remain always remain effective. That's why even the characterization setup that like in the input, let's say this is your input and in the output. So they use basically a tunable impedance matcher actually. So that is stub tuner or whatever like different kinds of tuners are available. So like those all the load pull measurement circuit, they use different kind of tuners at the input and output of your circuit actually. So basically that you like at each time you need to match tune those like those tuner circuits so that your impedance is matched like that output and input load impedance is matched for those amplifiers. Yeah, so that matching is yeah, so that matching plus delivering, then only it will can deliver the power. If your matching is proper, then only you can deliver the power. So basically, load pull means yeah. So then only you can fetch. Huh. Hmm. Yeah, very simplistic you can say, but like it's quite complicated thing, especially in the high frequency like that. You see like that crores of like costly equipments are there like that. It's like impedance tuner itself costs like 10-20 lakhs is easily actually, and that probe tips also like quite like that like you need to take yeah you need to prove like do through Smith chart you need to match the impedance. That live Smith chart you can plot, and that with that you can just match the impedance. So yeah, so that was the main so that was the amplifiers and like different kind of uh, like the gain flatness and also it's like the few more important parameters of amplifiers are important. So that is one is your linearity actually. So the linearity is linearity is like basically like what is your gain. Let's say if you are plotting input voltage, let's say this is your input voltage or input power versus output power. So if your transistor, your amplifier is linear, then the ratio of input power to output power will always be remain same actually. So this, in the ideal case, this will follow a linear line, and the slope is basically your gain. So that V out by V in is your gain. Now for practical purpose, this will not be infinite. Actually, you can't have very high gain throughout all frequency range or throughout the all point of like your signal input power and output power. It will not be same. So basically, like this, after a certain point, this will start saturating. Similarly, here it will start saturating. So that so like there is like one more important parameters in like the amplifier design is 1 dB compression point. If you see any data sheet of the your analog amplifier, there especially that RF amplifier, they give specify this 1 dB compression point. So this is defined as like the the input signal power at which your or output signal power like if you know the input signal power or output signal power at which your gain like deviates away 1 dB from your linear gain actually. So that is this is known as the 1 dB compression point actually. So this specify at like in terms of like what is the value of this gain, what is like how much output gain you can have, output signal power you can have, and basically like you can use for characterizing the amplifiers actually. So is this clear? So this comes because of the, like, if you use very large like input signal power, then basically your non-linearity will come because the your transistor will have non-linearity. So let's say if I explain you in the graph. So let's say this is your let's use a different one. So let's say you are varying the signal at this. So basically, like, see, now let's say your load line is this one. So now if you choose along this load line, if you are varying the signal at this, so this between this point, so depending on the VGS sweep you will do, so larger VCF will vary the your quotient point around this line. So largest VGF will cause this line around this line. See now, because now within this line or smaller line, your amplifier does not behave like linear actually. So there will be some distortion in your output signal, and as you know, like the distortion in the signal means like it moves away from the sine function, and that distortion basically you can model by like different harmonics present of your fundamental harmonic frequency. So basically those harmonics may cause your those harmonics can cause the non-linearity also. Those harmonics also can cause intermodulation, which we see in the next section. So those non-linearity, basically non-linearity because this the transistor characteristic as you move at the quotient point, that transistor does not operate within the same region actually, same linear region. So is that clear, or is there any doubt? Not even saturated, like, yeah, so even just like the different like at different, as you can see, like different, let's say you are operating at this line. So so you are operating at, let's say, let me draw it differently. Let's say you are operating at different point. So then basically your, yeah, so now let's say you are operating at different point. So as you can see, like this, as you are operating at, let's say, here or here, you are getting the signal. Let's say you are varying the signal here. So basically you are, like, see, like the at the transfer characteristic, this slope gives your R naught. So at each point the R naught is different actually. Right. So R naught is changing, basically that like then basically you have different gain profile actually. So, and even if you across you will move, so like the GM versus VGS profile will be like this. So your GM is also varying actually. So that also may cause non-linearity, and that generate the harmonic. But for like the small signal, actually you can if you are, like, let's say, like different region of operation you can have, like you can have the low noise amplifier, which like this variation around the quotient point you can assume linear actually. Then basically you will have the linear only. Then basically quotient point will cause a different gain, but in the power amplifier basically you move around the quotient point very large variation or sweep, that will cause a distortion and non-linearity, and that will lead to your this 1 dB compression and other effect in your transition amplifier side. So is that clear? So what is the doubt? Huh. Going in saturation, yeah, kind of. Huh, that, yeah, that also you can say like that. It's not linear. It's not non-linear. Yeah. So that also like cause like bit of non-linearity. Yeah. So that is also one of the regions. Actually. Yeah. So basically, uh, so this so 1 dB compression point is basically defined as this like where your gain differ from 1 dB from the linearity point. Actually. So then other is the IP3. So basically, so this is known as the IP3. So it is known as the third order intermodulation product. If you see the data sheet of your analog low noise amplifiers and other amplifiers, even power amplifier, if you go to mini circuits and those analog amplifier circuits, you will see this. So basically it is defined as basically your like the third harmonic you will generate. So basically if you have, let's say if you have a circuit has a linearity, so let's say if you are giving a signal of, let's say, two frequency you are giving, let's say two band of frequency, x of t is, let's say your input signal is cos omega 1 t plus a2 cos omega 2 t. Let's say you are giving two tones to the your amplifier. Now output which it is generating, that is a let's say function of alpha 1 a1 plus something, some factor cos omega 1 t. So this is the fundamental frequency of this signal plus alpha 2 a2 some other product terms cos omega 2 so this is your desired signal. What happens is, also there occurs the few more signal, that is like 3 by 4 alpha 3 a1 square a2 cos of 2 omega 1 minus omega 2 t plus 3 by 4 alpha 3 a1 square a2 so a2 square a1 cos of 2 omega 2 minus omega 1. So all this extra term which comes, so this extra term, these are known as like the third order interpolation, because this comes from the third order harmonics. So like that, so so those intermodal modulation product, what difference actually is. So suppose you have a signal, like you are feeding to amplifiers and you have a signal which has a component as, let's say, this omega 2 frequency omega 1 omega 2, like these two frequency only you have signal, but at output you are having these two frequency also, plus there are few more frequency based on the up. So this is 2 omega 2 minus omega 1, and this is 2 omega 2 minus omega 1 minus omega 2. So these extra frequencies, basically extra tone, can order like can impact the other channel. Let's say if your channel is within this region, so basically this second order like the harmonic may impact your actual signal which is occurring in this region, or actual signal which is occurring in this region. So this is known as the intermodulation actually, because of the your other harmonics or other non-linearity, your actual signal which actual channel signal which is within that channel, that get disturbed, that is causing your intermodulation. So that important like that is important. So like yeah, huh. That is intermodulation. So you want intermodulation this frequency as low as possible. The lower is the strength of your intermodulated signal, the better you will have your characteristic. So this this basically it's decided by your third order intermodulation product. So basically, if you plot output gain versus input gain, so this so this let's say this is your output gain versus input gain. This is your normal first order gain profile, and then there is different kind of like the because of that third order intermodulation, there is another gain profile like this. So now if you so the third order intermodulation product is find out by like this third order intermodulation, if you line this line if you extend and this line if you extend, then basically where these two lines meet, the gain at that point is basically your third order intermodulation. Actually this is at the horizontal, like this is known as the IIP3 actually. And this basically this related to this is around 10 dB difference if you calculate. And that basically like this, if you take the ratio of this, so where from this to this, so you will see like that A out of IIP3 at the IIP3 point divide by the A out at 1 degree. So this divide by A out. So this P out at 1 dB divide by A in as IIP3 divide by A in at 1 dB. So you will define that this is 1 dB compression point. Like you take this as a 1 dB compression point, and here also you take this as a 1 dB compression point. Like that, basically A in and A out you take, and basically that ratio you can compare it with respect to 1 dB compression point, and that will come out to as 3 by 4.145, and which is, if you convert to dB scale, this is equal to 10 dB. So basically your this IIP3 point and this is around 10 dB actually, right? Is that clear? Yeah. So you can just find this compression point, just where this 1 dB compression point is there. You move 10 dB above the your output characteristic, and you extend this linear line, and where this linear extension line intersects with the 10 dB point, that is your the third order intermodal modulation product point. And that basically you can just superimpose based on your third order intermodulation product gain line, and that basically different frequency or any gain value you can achieve what is your third order intermodulation product. So any region of operation you can obtain that. Huh. So basically, yeah. So based on your like the saturation point, it will move away from the 10 dB actually. Ah, yeah. So basically, no. So like these points, the larger it will be, so lesser is your intermodulation product. So let's say this curve, if let's say just wait. So smaller the smaller this third order intermodulation product like this, the larger it will have like farther it will have, like you can have much larger gain so that it does not cause inter modulation with the 10 dB, right? Huh. And less, yeah. So you have like the higher the 1 dB compression point. So basically, if you move here, then basically your intermodulation product will be like that IIP3 will come at very large input signal power. So you can amplify basically like large input signal power based on that. So basically, this is used to design your amplifier based on your how much inter modulation product at what gain you want, or what input signal want, what output gain you want, what is the your output like 1 dB compression points, like that. All design parameters condense into you need to optimize those parameters. Mhm. Yeah. Mhm. The gain high, yeah. So gain, not only the gain, like that, how much output power you want. That is like, so the y-axis is output power. So higher the output power you want, like that, like you need to design bigger amplifiers and more compensation kind of circuits actually. Even the temperature compensation and those things you need to do. So achieving higher and higher gain is difficult actually. You need like more huh, that is the requirement. Yeah, yeah. Mhm. Yeah. Practically, basically, no, no. Practically, you need to design such that your all those your harmonics and those are reduced actually. So basically, like the suppose your temperature is causing your nonlinearity in your amplifier. So you design a temperature compensation circuit, or you are operating in a region where like the intermodulation product is high. So you can design with the region which has the lower intermodulation products and those, like that basically Smith charts and those things you need to optimize it based on your, yeah, yeah, different region, like where like what cause lower intermodulation product. But that won't be simple. There will be some trade-off corresponding to the that. So that is not like that simple. It's like 10 or 20 or 100 different parameters you need to lay out. You need to take assumption of certain, and then you start sweeping the others. So which are the relevant parameters for you? So with that, should we move to the problem solving session? I think it's already 8:15. So yeah. So do you have any other doubt? Okay. Oh, okay. Fine. Okay. So you have any other doubt from previous session? I think you were messaging around before. Okay. Okay. Fine. Okay. Yeah. Fine. Okay. So then let's just move to next. Let's just move to problem solving session. So then basically, this this is for a microwave oscillator. So for a oscillator actually, so So the oscillator, you might have heard that Barkhausen criteria. So basically, oscillators you can design in the positive feedback. So if you connect the amplifier, let's say this is a AV of gain, and if you connect a positive feedback from output, so this is basically so this is beta of j omega, and if you collect, this is V in and this is V out. So basically, like that, basically, your this at this basically your V in plus uh, beta omega V out is there. So that so basically your V out. So you can write as uh, V out is equals to AV times V in plus B times j omega times V out. And if you take V out term to the left side, so your V out will become V out 1 minus beta times AV. I am just just taking the times times the AV times V in. And if you calculate this V out by V in, basically this is known as the AV times 1 minus uh, beta times AV AV, and this like the gain of this like positive feedback circuit is this. So to cause the oscillation actually, so there is this bottom term should go to zero. So like this comes from the control system. Your like poles of your transfer function should be equals to zero. Then it will cause instability and it will cause the oscillations actually. So then basically this beta times AV equals to 1 is your this Barkhausen criteria. So then with this basically like this is known as the loop gain. So your loop gain product should be equals to 1. Also the phase relationship you can I think it's just maybe I missed. Yeah. Yeah, so this phase relationship also should be negative. So basically, like this device actually you can say like the oscillator you can model by the resonator only. So basically, this you can model as a resonator connected to a noise circuit to the active circuit. So basically, all this like this, let's say this side is the load impedance ZL and this side is the input impedance ZN. So the criteria for this is basically so criteria is Z in at A naught comma omega as a function of omega equals to minus ZL equals to minus ZL of omega. Also, the other criteria is gamma in at a naught comma omega equals to times the gamma L times omega naught equals to 1. So this is the loop gain and this is the phase matching condition actually. So that basically like this condition only achieved by the phase matching condition, and this because this beta and AVs are complex in the AC signal. So basically this both the phase matching and impedance matching condition you need to obtain. So for oscillation your Zin it should be equals to minus that time Zn. So if based on that, if we try to solve this problem, so for a microwave oscillator, so this is given as for a microwave oscillator, what is the input impedance if the load impedance is this thing. So this the load impedance, the input impedance is basically negative of your load impedance. So that is equals to minus 45 minus j times 100, and this will become minus 45 plus j times 100. So the correct option will be this one, third one. So is this clear? Yeah. So in huh. Like, yeah, so the condition required to start the oscillation. So basically, in the previous, I think second lecture, we discussed the delta and k and gamma L and gamma out conditions actually. I think it's in the seven, yeah, I think it's seventh lecture or seventh or sixth session. We considered like what is the gamma L, gamma K, and all those signal flow graph we discussed. So basically, in that, what is the condition for condition for instability? So basically, that condition for that there it was delta for stability. This was delta greater than one, K greater than one, and gamma L gamma out was less than 1. But for instability, the condition will be reverse actually. So delta less than 1, K less than 1, and gamma L gamma out greater than 1. So the condition required to start oscillation will be this one. So the correct answer will be delta less than 1, K less than 1, and gamma L gamma out product open loop reflection coefficient product should be greater than 1. So for detailed derivation, you can refer to the previous lectures and previous slides. Okay. So is that clear? Actually, let me just search the key. Uh, so uh, so yeah. So this see like the for this for like for the stability condition. So this the conditions was the conditions was the uh, the let me write this k was this 1 minus s11 mod square minus s22 mod square plus delta square divide by 2 times s21 mod s12, and delta was given as s11 s22 minus s21 s12, right? So these are like the criteria for like the storm criteria for like the stability. For it was given that your your k must be greater than 1 and delta must be greater than 1, and delta must be greater than 1, and your this product should be less than 1. But in this case, you we want instability. Actually, will oscillation will occur only when you you provide the loop gain greater than 1. So a reverse condition will happen when you you otherwise saturate these bounds. So that with that you will achieve the oscillation conditions in this way. Is that answers your query? Hmm. No, no. K greater than 1 for stability actually. K and delta, yeah. But for instability, you want oscillation when your system is not stable actually. Yeah, then oscillation will get. Delta, this is for, this was the condition for stability. But you want oscillation, you want unstable. Yeah, K less than 1, delta less than 1. Yeah. Yeah. Okay. So then the let's move to next problem. So in this problem, it is the relation between A out IP3 and A out 1 dB equals to. So basically, like the ratio of A out IP3 as we have driven. So basically, this is let's say this you draw. and the A out IP3 is this one. So this is A out 1 dB is this one, like the gain at 1 dB compression point, and your IP3 point comes here. So basically, as we have done, this is A out at IP3. So that basically, what is the distance that we calculated? Like if you drive, this ratio will come out as around 10 dB actually. So or square root of 4 by 3 divided by 0.154, I think, which is equals to the 10 dB, right? So the correct option will be B. Is that clear? Yeah, yeah, yeah. This is the standard. Like once you write the equation for, I'll tell you like how you can write. Just uh, yeah. So basically, if you calculate the basically your you need to calculate the power of like third order intercept point, and basically the your like the third order intercept point and your gain at your fundamental frequency actually, that we if you equate, then basically you will reach at this corresponding to this value. So so basic, and your the power at 1 dB compression point. So that basically you can yeah, like if you take that ratio, then basically you will see like that it's always 10 dB. So that yes, yeah, this ratio comes to 10 dB. So this okay. So uh, with this, let's just move to next problem. In general, a frequency compensation technique, the like basically, let's say what you do in the frequency compensation. Let's say your gain is different at different frequency. Let's say this is the gain is higher. Let's say this f2. The gain is this one. F2 the gain is A2, and F1 gains in A1. So basically, you put a circuit like such that, like the compensation circuit such that, which decrease the gain at this frequency. Like you put a output circuit which has a response like this. It has a response like this. So now it has a response like this. So basically what will happen, at the this frequency it will reduce the gain, and at this frequency it will like increase the gain. So basically then your the gain will get flat actually within these frequency ranges, because that this is compensating it. So basically like that, uh, at higher gain frequency is filtered. So basically higher gain frequency you filter, you pass, and lower frequency gain filter frequency also you filter. Like one is you attenuate or amplify, like the like depending on whether higher frequency gain is increasing or decreasing, you can just attenuate or amplify, like depending on which region you are working. So the so this the both so this the also uh, higher gain frequencies filter and amplifier responses filters to get constant gain in a broadband frequency. So basically, like you want a constant gain, so you design corresponding compensation circuit. What is the slope of this gain change actually between those two frequency point actually. So basically, if you design the like the compensation circuit such that like that, it at each product it will just give the gives you the constant flat gain. Or log profile, basically it just add the, like this add up in the log domain, it just add up, and in the normal linear scale it will just get multiplied. So you are creating a multiplier which will give the constant gain at each of the frequency. So this will give flat gain actually. So the correct option will be the first one is correct, and the second one is correct. So in general, frequency hmm, hmm, huh, broadband frequency. So basically, uh, so that next is like this is the state, like the overall, what is the overall drop in gain when one of the amplifier in balance amplifiers fails. So basically, like that will like that standard answer for that is just it just fall. So balance amplifier is made like this actually. So this balance amplifier is like this. You use a hybrid coupler here, and then one amplifier, and basically again you use a hybrid coupler actually. And this side, like the reflection in this side is dumped, reflection in this side is dumped, and your input is this one, output is this one. So basically it just like if one amplifier like stopped working, so you will see, like if you I think you can refer to the text, it is 6 dB gain, 6 dB drop in the gain actually. Because that power become just half, and square if you take, then you will get your total like 3 dB in each, and in terms of signal power gain it will become 60. Big, huh, yeah, amplify fails, huh. Hmm. Yeah. So, like this, if your one amplifier, let's say this is the balance circuit. So basically, like this at one port, it add up the power, and in other port, it add up. If this amplifier fails, so basically, like this two ports, this power add up will get fail actually. So each will cause half 3 dB drop. So the total power loss, like it will be around 6 dB. The loss at the both the port actually. Okay, not working here. So yeah, so basically, like this one hybrid coupler, there will be half loss because two arm only working, and then the gain amplifier, then other hybrid circular, there will be half power loss because see hybrid coupler, the power is divided between each half. So like once this other arm is not working, you will not get like like the correct addition of power actually. So basically, this other, like once this amplifier stopped working, so this amplifier stopped working, then basically this power loss. So you will see like this hybrid coupler will cause 3 dB loss here, 3 dB loss here at the output. So your total loss will be 6 dB. Okay, so yeah, yeah. So at 1 dB compression point, which is statement is correct? The output power level is increased by 1 dB from the earlier. No, it's decreased by 3. Yeah, so the correct option is B1. So this is very simple. Uh, what is the conduction angle of class C amplifier? So basically, as we have discussed here, so the class A amplifier has full 360 degree. Let me draw it correctly. So if you draw the conduction angle, so this is the theta. This is, let's say, minus 180, and this is 180, and then you will draw this. So basically this will get like this. You will see this is complete cycle, right? And this like at the minus 90 degree, then basically your this will get clipped. So basically this will follow like this, and this is your class. This is the operation, which is this operation. This is your class B operation just at the 180 degree. This is your class B operation. This is your class A operation. Between this is class AB operation, and beyond this like angle, that is your class C operation. So your conduction angle is less than 180 degrees. Your basically class C operation. So the correct angle correct is your alpha is less than 180. So that basically and the which type of feedback is used in the oscillator. So negative feedback, as you have seen in the like op amp case, like all those are negative in the negative feedback circuit. If you want to make the oscillator based on the op amp, you just apply the positive feedback, and you achieve the loop gain beta AV equals to 1, and the phase matching condition also you did. So total phase should be equals to 180 degree. So that in these two conditions, if you achieve, then basically you will achieve the all the Barkhausen criterion, and that with the positive feedback you can achieve. So this the correct answer is positive feedback. This is just simple. You may have seen. Uh, so like the So this basically the reflected power in the balance amplifier implemented using power divider. So basically like how you divide the balance using the power divider. Basically this is suppose input line, then there is lambda by 4 transmission line. Simply this is and then that there is 50 ohm matching. This was even we see this circuit in that, and basically then you will see the lambda by 4 delay line, and one amplifier is there. Then basically you have amplifier, and then lambda by 4 delay line is there. Then basically this again you just use the power combiner actually. That basically this is by lambda by 4, this is lambda by 4, and that this is R, this is R. So the all the reflected power, so basically all the reflected power, as you can see like was dropped in this resistance actually in the impedance matching circuit. That's why all this like all the reflected power will be lost in this resistance circle in the power divider. So this is power divider, this is power combiner. All the reflections will be reflected power will be like consumed by this resistor. So the correct answer is the second one, because these delay lines and these amplifiers assumed to be lossless. Even this delay lines is assumed to be lossless. So all the reflected power will get lost in the only the resistive component is that resistive like a circuit between the power divider. So is that clear? So yeah. Basically, which of the following is called as a switching amplifier? Class A is not the switching amplifier because that linearly you need to operate. So basically, like in the switching amplifier, what you do, basically, like you suppose, like you, let's say a diode which conduct in only one direction. So you use two diode actually connected in reverse. Like the for positive cycle you use one diode and negative cycle you switch between the diode actually. So those are basically the switching amplifier, and those can be can be in the like that can be like the conduction and angle between that will be less than 180 degree only. So that can be classified in the class E and class D amplifier. That is just the theoretical questions. Yeah. Like for reference, you can go through the different classification of different kind of power amplifier. Even like lot of switching power amplifiers are used in especially your SMPS in those kind of circuits actually. Class C uh, Class E basically you want very less time conduction. So basically you control through like different. No, I also don't know much about those switching amplifier, so I don't have much understanding of it. But okay, so I you have any doubt other than this? I'll just have completed this session. Yeah. Okay, okay, fine. Thank you so much for listening. If any other like if you have any other doubt, you can ask. I'll pause for some time. Otherwise, we can end this session. Uh, okay. Ah. Just let me just me let me just message you. Actually, let me just stop the recording. Uh, because otherwise it will be public.